So in the previous video we talked about the axiom scheme of comprehension and the power set axiom. In this one I'd like to talk about the axiom of infinity. So this is the seventh axiom, the axiom of infinity. This is essentially saying that there exists a set within our universe that behaves as the natural numbers should behave. So formally this states that there exists a set, call it I, such that the empty set is an I, and for all other sets X, if X is in I, it implies that X union the set containing X is an I. So the shorthand, I guess, to remember this is that the natural numbers is a set. Now this doesn't really look like the natural numbers though, but it'll look more clear if we use the following convention. So denote we denote by the empty set. In this context we denote by 0, and then we denote by x plus 1 to be equal to x union the set containing x. Then what do we have? Then the previous axiom can be stated like following. We have that there exists an I such that 0 is an I, and for all x we have if x is an I, it implies x plus 1 is an I. So we'll have to flesh out the details in another video, but that's the general idea. Some definitions, just to make it easier to talk about this. So definition, given A, if so if A satisfies the property of 7, so in other words, if A satisfies the fact the empty set is an A, and for all x, if x is an A, it implies x union if this condition holds, we say A is inductive. And this is alluded to by the terminology that we're using, but this property is going to allow us to do induction on this set. And again, we'll have to flesh out the details, but the reason why we're calling it inductive is that we're going to be able to do induction on it. Or there's some notion of induction that can be talked about with regards to this set. In the next video, I'd like to prove the following fact. So fact. And then I'll talk about some of its consequences for the remainder of this video. So the fact is that there is a minimal inductive set, and we denote this by omega. So in other words, what does this mean? This means that not only is omega inductive, and but we further have if we have another inductive set, we have that omega is a subset of I. So that means, at least with respect to size, omega is the smallest possible inductive set. Size is in air quotes. Informally, we can think of omega like this. So when I say that the natural numbers exist, I really mean the natural numbers in this case is going to be what we denote by omega. So informally, we have omega as equal to this set like this. So this is informal, where we have a convention where the convention is as follows. Any natural number, so any element of omega, is going to be the set of all things before it. Notice that this a natural number, the number of elements in the set n there are n elements. So we want, say, the element 7 to be a set with 7 elements, and in this case it just so happens that it's the elements from 0 to 6. But so examples, we have that 0 is equal to the empty set under this convention. But this also follows from taking that union that was supposed to mean plus 1. So I'll show you what I mean. So 1 under the convention is the set containing 0. 2 is going to be the set containing the empty set, and then the set containing the empty set, which is equal to the set containing 0 and 1. And then you do this, and so on. Otherwise, we can actually do it like this. So we can start with using So we can start with 0 as the empty set, and then we can apply the successor operator to get that 0 plus 1, that's going to be equal to the empty set union with the set containing the empty set. But any set union with the empty set is just whatever the set is originally. And this is what we considered. This is what we under our convention. This is what 1 was. And if we take 1 and we do 1 plus 1, this is by definition of this plus 1, or under the convention that we're using of what plus 1 is, we're going to get that it's equal to the set containing the empty set union with the set containing the empty set. What is this equal to? This is just going to be equal to the set containing the empty set and the set containing the empty set. That sounds, when I hear myself saying that, it sounds absurd, but it makes sense if you follow the brackets, I guess. And this is what we had. This is what our convention of what 2 was. If you rewind in the video. And maybe perhaps a more clear way to look at least the last example, we said that 1 plus 1, that's going to be equal to 1 union with the set containing 1. And 1 was by definition going to be equal to the set containing the empty set. So this is going to be equal to the set containing the empty set union with the set containing the empty set. And then we get 2. But you can continue you can do this forever, and in each case you're going to get that the nth natural number. So for all natural numbers. By natural number, I mean an element in omega. So for all elements in omega, we're going to have that n is the set of all things before it. Something like this. Just one final thing. We define a relation, an ordering. So we're going to define our usual notion of less than, which exists in the natural numbers. So actually, let's intuition. We want to have, for example, that 1 is less than 2, or that 7 is less than 13, etc. So we have to, what is it? And we know that in this particular example, we know that 1 was the set containing the empty set, and then 2, we want this to be less than the set containing the empty set and the set containing this set here. The set containing the empty set and the set containing the empty set. Well, notice that in this particular case, this set here is in fact an element of this set here. So 1 is actually an element of 2. Because this set here is appearing right here. So we define, we'll do this more explicitly. I'm saying this almost in passing, but we'll talk about it more explicitly later. But we're going to define for any natural numbers. We're going to use, I guess, the convention, or we're going to define the less than ordering by m is less than n if and only if m is an element of n. And again, this kind of makes sense, at least under if you believe me when I say that an element n is the set of all things below it. So if m was less than n, then m would appear somewhere in the set, and then therefore it would be an element of n. Okay, so that's enough about the infinity axiom. Well, in the next video, I want to prove that there is a minimal inductive set, omega. So in other words, there is a set that looks just like the natural numbers. So a slight digression, but then we're going to continue on with the replacement schema and the rest of the replacement schema, the axiom of foundation, and then the axiom of choice. So I'll see you in the next video.